In this video we're going to look at the always true or sometimes false questions and just try and see what we have already seen in chemistry where things might go against our common conceptions of how chemistry works, and just to broaden our understanding a little bit about exceptions to rules that we might think have no exceptions at all. So we're going to do them a few at a time and have a look at whether they're true all the time and whether we can think of any exceptions for the ones that are not. So question 1, atoms of group 2 have 2 electrons in their outer shell, and that is going to be always true. So you are going to do some more things at A level about atomic structure. You're going to get a bit more detail, but our idea of group 2 means 2 in the outer shell. We're not going to change that. Number 2, elemental oxygen exists as diatomic molecules. That is also always true. So whenever you're doing a balanced equation or anything like that, you want to be writing O2 and not O. And number 3 is also always true. We're not going to change the laws of physics. If 2 different ions have opposite charges, they will definitely attract each other. So that was an easy 3 to start with. And then we have number 4. So energy is released when ionic bonds form. And you should know that actually all bond making, so bond making is exothermic, i.e. gives out energy. And I know there's not a lot done in AQA GCSE about exo and endothermic in terms of bonds, but hopefully this will make sense to you. And bond breaking of any kind at all is endothermic. So where you've seen that before is solids, liquids, gases. We need to put energy in to go from solid to liquid, liquid to gas, and that's because we're breaking whatever type of bond there is in that substance, ionic bonds, covalent bonds, or just intermolecular forces or metallic bonds. So if we have to put energy in to break those bonds, then we get energy back out when we make them. The reason for that is that all bonds, every single type of bonding you do in chemistry, and we're going to do more about bonding this week. So a bond in chemistry, in case it's kind of gone over your head as to what it actually is an electrostatic attraction of some kind. So electro meaning to do with charges, static just simply meaning the charges don't move, like in static electricity. So we're not talking about a current flowing, we're just talking about 2 things, one positive, one negative, attracting together. And so if you were to think about 2 things that are attracted to each other, if you bring them closer together, they're going to attract together and they're going to give out energy when they do that, in the same way that if you brought magnets together, they would like pull each other towards each other and give themselves some kinetic energy. So energy is always needed to break covalent bonds. That's probably the easiest thing to look at. Number 6 is definitely always true, which means that the opposite, when bonds form, energy is always given out. And we're going to go back to this idea a few times in some of the other true-false questions as well. So any time that you're bringing together a plus and a minus, so that could be like a nucleus and an electron, or it could be in a covalent bond. In a covalent bond you've got a nucleus in each atom, and then you've got a pair of negative electrons in the middle, so they're attracted to the nucleus either side. In ionic bonding you've got a whole series of positive and negative charges all attracting to each other. So obviously if I want to break them up, I have to put energy in, which means if I'm putting them together, energy will come out. Number 5, an ionic compound. Ions are combined in proportions which balance out the electrical charges. It's a bit wordy, that one, but it's basically what you already know about writing a formula. Yeah, compounds don't have charges, whether they're ionic or not. And the reason they don't have charges is because we write the formula in order to balance that out. MgCl2 rather than MgCl, for example. So that's always true. There are no compounds. There's nothing that we call a compound that has a charge on it. We have some ions which contain more than one atom, like sulfate, but that's not a compound on its own. It has to be combined with a positive ion to become a compound. Okay, energy is required to form positive ions from atoms. So the reason I put number 7 in is because lots of people have this idea. So lots of people think, for example, sodium loses an electron quite easily. So lots of people tend to think that sodium ions are more stable than sodium atoms. So you've got this idea that because they have a full outer shell, which you've got to get rid of this idea because it doesn't explain a lot in chemistry at all, because it has a full outer shell, then it's more stable. But that's wrong. You might say that sodium loses an electron quite easily. So sodium loses an electron quite easily compared to lots of other things. Sodium is quite ready to lose an electron, which is why it's a reactive metal, and why it tends to react with lots of things at room temperature, because it doesn't need much energy to lose an electron. That is not the same as saying sodium ions are more stable, or that it doesn't give out energy when it loses an electron, because if you think of the sodium atom and its shells of electrons, there's an attraction there. That outer shell electron is attracted to the nucleus in the same way that the moon is attracted to the Earth gravitationally. If you try and move that electron away, you will have to put energy in. So we're always going to have to put energy in to form positive ions from atoms. So that is always true, no matter whether it's an atom that normally forms a positive ion or not. You do have to put energy in. You get energy back out in the reaction because then the ionic bonds form, which we just talked about, between the ions that are made. But you have to put energy in. It might only be a relatively small amount compared to other things. Doesn't mean that the ion is somehow lower in energy. Electrons shared between atoms are more stable than electrons not shared. I've got an awful lot of true ones in a row here. Yes, that is also true. So electrons shared between atoms are more stable. What we mean by electrons shared between atoms is we mean electrons in bonds. Why are electrons, and particularly in covalent bonds, more stable than electrons that are not? Because of the attraction. So you'll notice there's really big themes going on. They're going to go on all the way through your chemistry in the first year, definitely, where we talk about charges, attraction and distance between them. But if you've got two atoms, we've got a nucleus in the middle, then these two electrons that are in between the two nuclei have got a nucleus either side that they can be attracted to. So they are going to be lower in energy because they've got two things holding them there, whereas opposed to the other electrons that are not being shared and are in different parts of the atom. Remember, this is always just a model. If you're wondering whether the electrons somehow sort of like magically stay on this side of the atom, no, they don't. They do orbit round, but there are areas of orbits in between the two nuclei and there are areas that are not. So yeah, the ones that are being shared That just means that forming a bond is better than not forming a bond. Things will tend to form bonds. That's why they form things with full outer shells. Not to get a full outer shell, but to get those electrons being shared between two different nuclei. And then electrons that are closer to the nucleus experience less shielding and are more strongly attracted than electrons further away. I don't think I've put any that are false yet. So that's true as well. Always true, definitely. Just another attraction and distance idea. Compounds are more stable than elements. So if we were to take like a common example, sodium, highly reactive metal, reacts with chlorine, highly reactive metal, and makes sodium chloride a highly unreactive salt. So from our sort of traditional chemistry stuff, this one is usually true. Normally, when you make a compound, you give energy out, which means that if we were going to do a little energy level diagram, you would have reactants here, products here, and products would be lower in energy, hence what we mean by more stable. But there are just a few compounds that are less stable than the elements that they came from. So some of these compounds you know about, some alkenes. So for example, ethene is actually less stable than the carbon and hydrogen that it comes from. So you have to put energy in to make ethene. That kind of ties with the fact that we know that ethene is really reactive and will react very quickly with things like bromine to form a different compound. So that tells me it's not very stable. Lots of nitrogen compounds are also not so stable. So one of those examples is hydrazine, which is used in rocket fuel. Sounds like it's not a very stable thing. And the reason that a lot of nitrogen compounds are not very stable is because you have to break really strong triple bonds in a nitrogen molecule to make compounds. So there's more energy going in there than you necessarily get out when you make a lot of nitrogen compounds. Number 11, when atoms form ions, the ions formed have the same electron configuration as noble gases. So this is a good rule of thumb. We're not going to throw this out. We're definitely going to use the idea that you already know that group 2 make a 2 plus, group 3 make a 3 plus, group 7 make a 1 minus, group 6 make a 2 minus. And these are all, they would definitely form noble gas configurations. However, the groups aren't all the atoms that you know about, because you also know about, for example, iron. And you'll have done tests for iron 2 plus and iron 3 plus. You will have worked with their formulae, so you know that transition metals can form more than one ion often with different charges. Now if you can form more than one ion, they can't both have a noble gas configuration because they're different charges, so they've lost different amounts of electrons. And in fact they're not noble gas configurations. When you do more about atomic structure, you will see a little bit more about how transition metals work. They still form ions, and the reason they form ions is because ions can form ionic bonds. Ionic bonds give out energy. So they still do that, even though they don't have a noble gas. So that's usually true, and we're still going to use it for all of our normal groups. Groups 1, 2, 3, 4, 5, 6, 7, 8, we can predict. Obviously 8 we're going to predict doesn't do it, etc. Number 12, ionic compounds are formed when metals react with non-metals. So here again, we're going to say usually true. And well done if you could think of an exception to this. There's a couple that you've seen already at GCSE. So one of them is the ammonium ion. which you would have looked at when you did about fertilisers particularly, and ammonia, making ammonium salts. So for example, ammonium nitrate is a compound made of ammonium ions and nitrate ions, so it's definitely ionic. It will have all the properties of an ionic compound, high melting point, will be a lattice, it will be soluble in water, which is why it's good for a fertiliser, but it's not got any metals in it. Other way of looking at this is you have looked at also things which are covalent, like HCl, but when you put HCl in water, it forms ions. So these are two non-metal ions. That's why HCl acts as an acid. And then when you do A-level, you will also see that occasionally metals can make covalent compounds with non-metals as well. So there are some metal compounds that involve sharing of electrons instead. It's more of a scale between ionic and covalent rather than an always ionic, always covalent. But it's usually true, but not always true. And then number 13, it looks like I've grouped all of my usually true together. Within a covalent compound, all elements except hydrogen have 8 electrons in their outer shells. Usually true, because once we've gone past hydrogen, we're going to either lose electrons or gain it. We're going to share electrons according to trying to get a full outer shell. So group 6 can share 2, group 5 can share 3, group 4 can share 4. But if we looked at boron, boron is a non-metal, so it makes covalent compounds, but boron is in group 3. So when boron reacts with other non-metals to make a covalent compound, such as, let's say, BF3, what would that look like? Well, boron has got 3 electrons. Fluorine is going to share 1 each because fluorine's in group 7. Turns out that that's all the electrons we have. So fluorine has 8 in its outer shell, but boron does not, because if you start with 3, there's no way you can get 8 by sharing 3. The maximum you can get to is 6. It's still a stable compound because we have made bonds, and remember that these electrons that are being shared are more stable like that than they would be, and making bonds gives out energy, and that's why the compound has been made, not just to get a full outer shell. One thing to note though, for when you do start looking at dot and cross diagrams again, is all of the electrons are in pairs. I've drawn them like that deliberately. So although we are allowed to have less than 8 in the outer shell, and in fact there are some compounds where you have more than 8 in the outer shell for certain elements, which you will look at more in A-level, what you can't do is you can't have an odd number of electrons. So odd number of electrons is absolute no-no. You can't have more than you start with in terms of sharing. So if you've got 3, you can't have more than 6. If you start with 4, you will have 8, and so on. But we can't have odd numbers of electrons. So there are definitely still rules that you're going to follow all the time while you're looking at drawing covalent dot and cross diagrams, which we will do a little bit of practice of this week as well.